Welcome to the first in a series of video presentations entitled Getting to Know Cimatron Die Design. In this series, we will discuss features that apply both to progressive dies as well as transfer dies. We will look at creating a strip with all the different punches. We will consider what's involved in advanced forming conditions to analyze the part for wrinkling and tearing. We will also look at predictive springback and how that information then can be applied to deform the tool. And we're going to also feature Cimatron's powerful die design for creating custom die sets, factoring in punch clearances, working with catalog components, and also creating wire EDM punches, just to name a few. Our subject today focuses on data import, analyzing the part's geometry for formability, and also getting the part ready for die strip layout. We will start by featuring the wizards that are available for design. Simply select the appropriate wizard, in this case the one for progressive die design. Select the part that we want to create a strip of, and it could be more than one part as well, and then give it the appropriate name and location for a folder to save the information in. With that, we'll then step into the main interface. On the left-hand side, you see the tree for organizing the assembly and strip structures, and then on the right, you see the guide, which will guide us through every major operation of designing the strip. This part has multiple bending conditions. Under Analysis Tools, we will find Draft Angle Analysis, which quickly color codes the part based on a range of angles and sizes. Here, anything in red is considered undercut or trapped, whereas anything in purple would be vertical. Specific locations can be tagged to highlight the angle at that point, and then this information can be shared as a PDF file to communicate with the customer or other engineers. We will now look at the overall size and volume of the part. A quick measuring tool is available to find the size of rounds or measure distances and angles individually. It also finds the geometric center of the part, its overall sizes, as well as volume and mass. This information can also be published and output then as an Excel report, text file, or 3D PDF file. Going further, we will analyze the part's curvature. Using the curvature map, we will color the part based upon its different sizes of radiuses. This helps us to see the different bending conditions associated with the part. These different colors can be controlled by sizes and ranges that are fully customizable, and individual points can be tagged too to draw emphasis to that location. This information can be saved as a 3D PDF as well. Next, we will consider wall thicknesses. Ideally, we would like to have our thicknesses a constant size or gauge, but some areas may be thinner if the part's going to be coined. Here the part is a constant 0.074 thickness or 14 gauge. Individual points can be highlighted again for emphasis. Along with this comes the functionality of a dynamic clipping plane, which allows us to cut through the part in any section to see the wall thicknesses much more clearly. This clipping plane can be driven through any feature of the part, stopping wherever we wish, and a true 2D section of geometry can be created at any point. We're at the point now where we can begin adding forming shapes to lay out our die progression. These shapes can simply be a duplicate of the previous one, or in this case, the one part we're working with. Simply give it a name to define that station and the operation we're going to accomplish there. These different forming shapes can be right hand, left hand, or mirrored as we see fit. And here we're going to give it a working progression so that we have room to develop each of the different shapes we're manipulating. Now we will use the die skin command. The purpose of this is to select if our calculations for unbending are going to come from the punch side or the die side. In this case, we're selecting the die side of the tool. From here, we gather the wall thickness and store this information in what we call setup. Here you can see that we're working with just the lower skin. So with that, let's see what is involved then in setup. Here you see the material thickness has been stored and that there is an extensive library of materials already available. More can be added as the user sees fit. In this case, we'll select a common high-strength steel, and the different properties are now listed. These properties, along with wall thickness, will be used in our calculations. Here's a diagram of the different die plates and components. So the purpose here is to set how far we want our punch to go through the die steel and the different clearances associated with each of those die plates. Some plates I may be worried just about a slug drop, so there'll be a wider gap, whereas others I'm more worried about the shear. In addition to that, different punch and die configurations can be selected. The more popular ones are shown here by these different types. With that, let's select one with a straight die land or length to it, a die life, and then maybe select a relief angle. So we put in the factors as we see fit, and those become saved as the standard with which we will work as we progress through our die design. With that, we thank you for viewing this introduction on getting to know Cimatron die design. Next in our series will be forming and bending.